So shall we start the Professor Juan Rodriguez Carvajal's lectures, please?
Thank you very much. Well, today I will be speaking about representations, but thanks to Branton has given an introduction at a level which is quite good. I will present how we use the representations and which are the calculations that we perform, for instance, in BalsIreps. Let me just start. This is the outline of my presentation. A summary of group representation theory, what we call basis function of a representation, representations of the translation group, representation of space groups, little group, and the star of K. I will just introduce these kind of concepts. Then representation analysis in magnetic structures, and then I will be speaking about BalsIreps, which is a very basic use of representation for magnetic structures and also distortion modes, if you want, but in another approach different from isodistort. Let me start. Well, this is what Branton presented. In fact, a representation of a group is a set of matrices satisfying the same operation rules as the group elements. It's very simple. The concept is trivial. We use this notation. This is the name of the representation and also the name of the matrices. We put gamma of G, being G, an element of a group. And then this is the important definition of representation is this fact. The matrix of the product of two elements of the group is the product of the matrices of the corresponding elements. One important thing that you have to know is this: whatever group has in principle an infinite number of representations, because you can use different dimensions, etc., etc. And we have also equivalent representation. If you apply a similarity transformation applied to all matrices, that provides an equivalent representation. For instance, if we use matrix U that is generally unitary matrix is, means that the inverse of the matrix is the Hermitian conjugate. Then this is corresponding to an orthogonal transformation in any case. When we have this representation here and we apply the same matrix to all the matrices for all the elements, we get another representation because the aspect of the matrices are different, and this is an equivalent representation. One important concept is the concept of irreducible representations. Irreducible representation means that they cannot be made smaller. Then you have a big matrix, and for instance, if we come here, we have a representation, gamma, and of this group. And then, for instance, suppose that this gamma, we have is an arbitrary representation. I will use the other way of working with that, because laser pointer, is that not gonna work with that? Laser pointer, yes. I prefer to use my mouse because it's better. Then this matrix, for example, corresponds to a particular element, and after applying some kind of unitary matrix for transformation, similarity transformation, you can reduce this arbitrary matrix to block form, diagonal block form. And you see here, and if you can do with the same matrix the same operation, have matrices of the same aspect for all the elements of the groups, and then you can say that this representation is reducible because all these parts, all these small matrices that you have here, are can be decomposed in this kind of blocks. These matrices act in different subspaces. And we say that this matrix, gamma G, is the direct sum of these matrices. Here we have 2 times the same matrix, and this 2 times B and C. A, B, and C are, in principle, irreducible representation. This is the meaning of irreducible representation. We cannot find other unitary matrix that makes, for instance, this C matrix smaller than that, depending on the context. Then we write a formula in general. A general representation can be decomposed in the sense of direct sum. Direct sum means a block diagonal form in the so-called irreducible representation, which are the important concept of group theory. And here is the number of times the irreducible representation gamma nu is contained in this bigger representation. This is something which is important, and you will see that in BalsIreps, and you can explore all this kind of how we can reduce this representation. There is an important formula in the group theory, which is the great orthogonality theorem. Here you have the element AG of the representation nu, LM of the representation mu, different representation, different elements. This is a complex conjugate, and this corresponds to G, and we have a sum for all the elements of the groups. Then we have this nice formula, which is orthogonality. Then normally this is 0 in general. But except in the cases, this delta, Kronecker delta that you have here are 1. Then, for instance, one important concept of the representation theory is the trace of the matrices, which are called in the representation theory characters, the character of the representation. Then, if we take the character is the sum of all the diagonal elements of the matrix. This is important because the character is an invariant. When you have a particular representation, when you apply unitary matrices to convert to an equivalent representation, the characters are conserved. This is an important characteristic that is the way of recognize that you have the same representation, equivalent representation. You have that for the characters, and then that allows you to calculate this number, the number of times the representation gamma nu is contained in a bigger representation. You just have to apply this particular formula, and you calculate the number of times a particular representation is in a bigger one. These are, in summary, in 3 transparencies, what you have to know about general representation theory. What are the so-called basis function of a representation? Well, this is, you can read that. The element of the symmetry groups act normally in vector positions. When you have a space group, you have a vector positions that can be represented by matrices that correspond also to a representation. And but you can treat many different kind of problems with a representation theory. In an abstract way, you can consider that you can select a particular set of functions or variables, phi I here, at the 1 up to p, spanning a working functional space, W. These functions constitute a basis of this W space. Then, for example, the operator acting on functions associated to a symmetry operator that acts on vector positions when applied to a function of position vector is defined by this expression. This is very important to know that if you have an operator associated to the symmetry operator that acts on vectors in the direct space, acting on a function, then this operator corresponds to that exactly. Phi of G minus 1 R. And that corresponds to a new function. You transform functions using symmetry operators. When we have this set of functions defining a working functional space, the operator acting on one of the basis vectors give rise to a linear combination of the same basis vectors that you have here, basis functions. Then that defines a representation. The linear combination elements for the element G, this is just a linear combination. That is in fact a matrix. Then this matrix defines a representation. If we take another basis related to the initial one by a unitary transformation, we may get the matrices of the gamma representation in block diagonal form. This is the important thing also. If we starting with that and we apply a unitary matrix here and get here new functions. If this, the system of psi function is split in subsystem defining irreducible subspace of the working space W. If we take one of these subspaces, labeled for example by nu, the action of the operator OG on the basis function is exactly like that here. You transform and you use what you have here. These functions are now restricted to the different subspaces. Each subspace has dimension L nu here, in that particular case. Then this kind of function that define this functional space are called in general basis function. Up to now it's very abstract. It's not something that you can touch because this is the general way of defining the basis vectors or basis functions, sorry. And for each particular case, we can take these phi parameters as constant vector of different things. It depends on the particular problem, physical problem you are working with. You are using, for example, band theory, you will use, for example, block functions, etc., which are continuous functions. There is a way of obtaining the basis vectors. This is the so-called the projection operators. When you have an arbitrary function and we use a projector, this projector is defined by this up to here. This part acting on a function phi give you some function here. Then the function is maybe 0 or another function. When you get a function, this is a basis function. Then you can repeat for the different I here. I goes from 1 to the LV, and then you can obtain different functions that are basis functions in general. The result of the above operation is 0 or a basis function of the corresponding IREPs. And the index J here is fixed. Taking different values of the different J index here, you remember that IJ correspond to elements of the matrices. Provide new basis function or 0. This is what you know. The basis functions are obtaining using these projectors. Let us go a little bit further to see examples, less abstract than that. And then we consider, for example, the translation group. The translation group is an abelian group. That means that all the matrices that should represent the translation must commute. And the only way that matrices commute every time are if they are of dimension 1. Then the multiplication of numbers is commutative. This is the only way. You cannot have two-dimensional representation for the translation. Then the translation group, we will enter into the details of how to deduce that. But this is a way, for example, the operator of a translation here, you see that can be written like that. Operation on A1, repeated L1, repeated L2, etc., etc. And the only function that is able to do that, put in the condition, the von Karman conditions, is the exponential. Like, is the root of the unity, in fact. Exponential 2 pi with these numbers here. L1, L2, L3 correspond to lattice translations. And then you have here a series of numbers. If we have a crystal with N1, N2, N3 unit cells, the product of that is the number of unit cells that you have in the crystal. In such a case, you can define a vector K that correspond to different points continuously. In principle, they are continuous, but here we have if you put N1, N2, N3 going to the infinite, in fact, that they are continuous. Then these vectors, you see here this product, that correspond to a scalar product of a reciprocal vector in the reciprocal space, not lattice, but reciprocal space, multiplied by a lattice translation. Then the representation of the translation groups are these quantities that you see everywhere when you see, for example, Fourier decomposition. The components of the Fourier decomposition are the basis function of the translation group. You see here, 2 pi I kt. K is the label of the representation. Different Ks correspond to different representations of the translation group. One important thing that I will not detail here is that the most general form of the basis functions are block functions. Block functions are of this form, UKR exponential minus 2 pi KR with UK a periodic function. This is what you have to put. These are the basis function we use, for example, in calculation of electronic structure of materials. Well, then the K vector is very important because it's also the label of the translation groups. Then you can see, and Manu has presented that also, and in the Bilbao Crystallographic server, you can see how the different points that are important in the billion zone, just these high symmetry points. But in general, you have, for example, this is the first billion zone, then all the points at the interior of the billion zone, if you have correspond to different representations of the translation group. How are the representations of space groups? That is the important thing now, because we are working in a physical world in which the major part of the material are crystalline or crystalline, I don't know, and then you can use for working with the physical properties of materials, you can use a representation, and then this is one component of that is the representation of the translation group, because we are always working with space groups. Now we will see how we get this representation of space groups. We'll not enter into the details. The only thing that we have to say, for example, we know that the block function are basis function of the translation group. If you put a general operator in the test space group, and you associate the associated operator acting on functions. This is, for example, a block function if you want. You have this action transform the function. And then the important thing is that when you apply an operator like that, this is the demonstration, but it's not, I will not enter on that. The important thing is this is equal. I don't know why you see only one sign. It is an equal sign. That gives rise, these are also an equal sign. This is not minus. I don't know why it appears like that here, but well, it's the problem of the resolution of the screen. But the important thing is that you see here, you transform a block function to another block function with different k-vector, in which the rotational part of the operator is acting on the k-vector. This is the important thing also. The block function also serve as basis function, but the representation are no longer one-dimensional, like in the space in the translation group, because the block function whose wave vector are related by a rotational part of G belong to the same subspace. This is one important concept also in the theory of representation analysis is the concept of star of K. The star is because you have seen before in the presentation of Branton several K vectors that have, when you apply symmetry operators, you have the aspect of a star, because you have rays that are going from the origin outside, and then you have the different Ks. Then this is the star of the K vector. You have a primary K vector. We can, for example, call that K1. And then if we apply the symmetry operators of the space group to the K vector, just the rotational operator, then you get K1. These are just the coset representative. But in general, you can put that. And at the end, you arrive to a finite set of K vectors that are related by symmetry operators of the original space group. Then the Ki vector here, if we know that, are called the arms of the star. The number Lk is less or equal to the order of the point group G0. The G0 is the point group associated with the space group. The set of elements of G leaving the K vector invariant means that when you apply that to K1, that gives K1 or K1 plus a lattice vector correspond to a subgroup of the space group, which is called the group of the wave vector of the propagation vector group of the little group. This group is always a subgroup of G, G1. This is the group of the propagation vector. It's always a subgroup of the space. Then the whole space or point group, little cogroup, can be decomposed into cosets of the propagation vector group. You can write the space group is GK plus G2, JK, etc., etc. Then these are the terms of the coset decomposition of the space group. Then this element, J2, G2, etc., are not belonging to GK, are different. Because if it was on that, it doesn't appear here. And you have, in general, the arm L of the star is JL for K, multiplied by K. Then you have a series of K vectors that constitute the so-called the star, or the K vector. Then for studying the general representation of space groups, we need to know the representation of this smaller group, which is the K vector, the the group of the propagation vector. Then we want to construct this kind of matrices that are irreducible representation of the group of the propagation vector. We need to know the matrices only for the coset representative with respect to the translation group of GK. Right? Then normally the translation group in principle is the same, and you have these are the composition of GK in coset with respect to the translation group. Then we need to know the matrices corresponding to G2, G3, etc. Only that. And we have to construct these kind of things. For a general element of GK, you see immediately that for this element belonging to the GK, another translation, the only thing is multiplied by this phase factor that correspond to the representation of the K vector of the translation group here. Then you have this formula. And the problem is to determine just these matrices in which you have only translation that are not lattice translation. Then, for example, you have a glide plane or a screw axis, etc., etc. The matrices can be easily calculated from the projective or so-called also loaded representation that are tabulated in the Kovalev book. This is quite old now. Or in databases, for example, of the isotropy suite. Here, this is much more convenient than consult the Kovalev group. The Kovalev group is a mess when you have to find which are the matrices, these small matrices. Then the rest of the matrices. Then in the isotropy suite, you have the representation, complete representation, all these. Then this is what we need is to use these matrices that can be obtained using tables, using programs. For example, BalsIreps has an option that uses the SAC method that was implemented in CAREP, and we use that in BalsIreps in order to obtain the representations. But can also read the database of isotropy and use the matrices provided by isotropy. Well, you have to keep in mind that the representation of GK and G is the full space group, are not the same. Well, we call the dimensionality of the gamma K nu is L nu, for instance. The basis function should be, in general, independent of the problem we are treating, are block functions like that. This is written down. Here, there is no problem because when you apply the symmetry operators of GK, K is not changing anymore because otherwise the operator you are using doesn't leave invariant the K vector. This is why we are using the GK as the basis, because there are no transformation between different Ks. Then using the element of G not belonging to GK, one generates other set of basis functions that constitute the basis functions of the representation of the total space group. This is the thing. I will not enter into the detail, but you have to know that there exists a formula, which is the induction formula, that constructs the representations of the full space groups in terms of the representations of the GK of the small representation of the propagation vector group. This is a little bit, seems to be a little bit complicated, but don't worry about that. The people that are interested in learning all this kind of thing can study the different books existing in the literature in order to understand a little bit better that. But what is important here you see you have two indices, L and M makes reference to K vectors, and I and J make reference to the indices of the small representations of the propagation vector group. This is something, well, You have to forget a little bit that, but you have to know that the representation of GK and G are different, but we can construct the representations of the full space group from the representations of GK. And this GK, this representation can be found in tables, can be calculated, but now we have a computer for doing that, and that's not a problem. What is the interest of this kind of theory for magnetic structures? Like for whatever kind of physical problem in which symmetry is involved, the representation theory is important. For example, we can construct a reduced representation of the propagation vector group by selecting, for example, in the case of a magnetic structure, the atoms of a particular Wyckoff position in the space group and apply the symmetry operator to both positions and axial vectors for the case of magnetism. You can put displacement vectors in which you apply that to polar vectors, and then there is for studying distortions. If we do that, for example, this gives rise to the so-called magnetic representation of dimension 3 Na, being Na the number of atoms in the primitive cell for the given Wyckoff position. You have a representation, you can construct a representation which is 3 times is because we have X, Y, Z, and N is the number of atoms that you have in the primitive unit cell. That constructs a representation. When you do this calculation, just applying the symmetry operators can be very simple. Just for positions, you can number the different elements of the Wyckoff position 1, 2, 3, up to Na, and the XYZ, you know that. And then when you apply to a particular spin, for example, in a particular site, a symmetry operator, then you have to multiply by the rotational part of this operator, multiply by the determinant also, because it's an axial vector. And you change the number. For example, you apply that to the atom number 1, you transform that to the atom number 3. Then you have some kind of permutation and things like that. And in fact, the representation, this magnetic representation, can be represented as a direct product of the so-called permutational representations and the axial representation. Axial representation, in fact, is, in the case of for magnetic structures, you have a series of symmetry operators, and is the product of the determinant by the matrix representing the action of on the magnetic moments in particular. And then the permutational is the atom 1 transformed to atom 3, the atom 2 transformed to atom 1, etc., etc. You apply for the particular element. We will see that in detail when we will look the output of BalsIreps, just to see how it works. Then we construct in general, for this magnetic representation is in general is reducible. It's a big matrices, the dimension is just 3Na, and you can decompose that in irreducible representation of the propagation vector group. And you can calculate the number of times some particular representation are contained in the magnetic representation. Then, in fact, in our context, in the context of magnetic structure, the basis functions for each IREP and each sublattice of a Wyckoff site can be calculated by using the projection operator formula that we have seen before in a general case. Then the basis functions are, in our case, constant vectors of the form 1, 0, 0, whatever, vectors, with component refer to the crystallographic unitary frame, in our case, this is what we obtain, attached to each sublattice. These constant vectors, then you can put whatever value before that. For example, 100 is the same as 8. You can normalize that as you want. They are just direction in the space. Well, I will skip this. It's a little bit complicated. It's just the way of what we construct that. But I will not explain that in detail because it's a little bit complicated and cumbersome. Then you start, for example, this is a vector in which we have a atom number 1, x, y, z, etc., etc., and we have a 1 and the rest is 0. Then we use this kind of vector, unitary vector, to apply the symmetry operators. But let us skip that. What is important, this function, the matrices of the magnetic representation can be calculated exactly from the matrices of the permutational representation, which are here, and this delta vector, which is related, this part here, epsilon, this term that we have here, multiplied by this delta, Kronecker delta, correspond to the so-called permutational representation, is here. You see, this is the permutational representation. This is a dimension Na by Na. Na is the number of atoms in the primitive unit cell. Then you have that. This is, in general, they are complex, but it's permutation representation. And the axial representation is, as I told you, is the rotational part of the operator representing a particular element of the group multiplied by the determinant. When you multiply these things, you get the magnetic representation. Then you can calculate that without looking. You can do that by hand if you want. It's more intuitive. And then Berthaud, who was the first using a lot representation analysis for studying magnetic structure, he was doing all time pictures, and this spin transformed to this, etc., etc. You can do that, but you can do in a computational way, just put in this formula, and then clack, calculate, and you calculate everything like that. Then you can also calculate the basis function of the irreducible representation of GK, just using the projection operators, as is the formula that we saw below before, for a general case, and then we can apply that, and the basis vectors are calculated exactly using this particular formula, which is complicated, but can be programmed very easily, and then you get the basis vectors. What we call atomic component of basis function, this is what the people can see more easily, is constant vectors that are proportional to this quantity. For example, this is one of the basis functions. Of course, if you change alpha here, you will see this is the matrix, the column matrix of the alpha component of the matrix H. Each H is the rotational part of the operator. When you apply this formula, you get a vector, a constant vector, normalized in a particular way. If you don't take care, you see that I have put here the symbol of proportional to say that you can normalize them as you want. And then these kind of vectors here, which are characterized by the K vector, the particular irreducible representation we are considering, which is new. Lambda is something that goes from 1 to the dimension of the representations of the sublattice S of the site J. Then you have all this information here, and you can calculate easily the basis function using this formula. For the case of the space group, you can do the same, and we can construct also the basis functions using the induced representations. One important thing here is up to now, we have considered only IREPs of the little group. In some cases, we can add more constraints depending on the, using the representation of the whole space group, of the extended little group. The extended little group is a concept which is quite interesting, that is mostly promoted by the people that were working in incommensurate crystallographic structure in order to bring together K and minus K, and then, because you can have, for example, in GK, no operation that transform K to minus K, but you have to use it. Then this is the reason why we can use the concept of extended little group, which are, for example, is equivalent to GK, or if there is no operation within JK, you have to add another operation which is not in GK, but transform K into minus K. Well, these are a lot of formula that you just to know that the extended little group, it is correspond to a part of the full space group in which we add to the little group the operator transforming K into minus K when minus K is not in GK. Then suppose that the operator G minus K that does not belong to GK transform K into minus K. Then the extended little group is like that. This is the composition of the extended little group in terms of the little group. And the representation of the extended little group has dimension at least 2 times the dimension of the representation of the propagation vector group. And then this is a particular case of the general expression of the induction formula for constructing the matrices of the full space group. Well, then you can study that in the literature. You can find the way of working with that. And then what the, let me now tell you what happened. For example, when the dimension of the reps is higher than 1, the list of possible basis vector may be quite high, some over lambda below here, for example. This is the Fourier coefficients that Javier Campos was explaining yesterday, I don't remember when exactly, but, or yesterday or before yesterday, the Fourier coefficients of the describing a magnetic structure can be written as a linear combination of the basis vectors. This is the important thing here. And then if you have a higher dimension, the concept of isotropy groups is crucial. In BalsIreps, we don't use that. It is the user who has to know how to work in order to find this thing by hand. In isotropy, everything is taken into account and then is classified, all the isotropy groups. Then isotropy subgroup is formed by the operators that leave invariant a particular order parameter vector. You remember a vector, eta here, corresponds to an abstract vector in the space where the representations act. Irreducible representation can be applied to vectors of the same dimension of the representation themselves. Then those elements of the group that leave invariant these vectors constitute a subgroup. And then these are called the isotropy subgroup. And then one thing that you have to know is it's a systematic study of isotropy subgroup is not implemented in BalsIreps, but you can use isotropy software suite to do the work. Then this is a few words that I wanted to tell you about that, and then I think it's enough for working with BalsIreps. And then we will see in the output of BalsIreps many things that we have written here in form of a general formula. And then it's not very clear for the people, because for understanding that you need some time for learning. That is cannot be done just in a talk like that. Well, let me now, I will show you BalsIreps. I wrote BalsIreps a long time ago for myself, also before trying to construct models for analyzing my own data. And then I put that for everybody. But, of course, at that moment, it was not dedicated to symmetry by itself. I was working with doing experiments and analyzing data. And then the concept of isotropies of groups and all this kind of thing, I didn't use that. But you will see how you can do that yourself. Well, BalsIreps, when you open BalsIreps, it's just an interface, very simple interface for the program. And this is, in fact, BalsIreps GUI interface. BalsIreps can be invoked also from the command line. And this is just a program that runs. Then for entering the BalsIreps, you have this is what you have. In principle, you have to fill only this part here. Then you have to provide a code for the files. Here, I don't know what I have put here, but well, anyway. Code of the file, IREPS database, well, it doesn't matter. You have to select a working directory in which the files will be output. You have to provide a title that is not used at all by the program. You have to provide the space group symbol. Here we are talking only of crystallographic space group. In principle, you can put whatever setting of the, well, I have a list of 600, I don't remember exactly, 604 different settings of a space group. And then you put that in a way in which you have spaces between the symmetry directions. For example, PNMA here. You put the K vector. Here is numeric. It's not list from the, but you can, of course, have a look on the Bilbao Crystallographic server as Dimitri shown yesterday and select the good point. But in general, when you are working with Neutron diffraction, you have a unit cell and you've determined the propagation vector and maybe something which is equivalent to another one which is not in the database. This is a problem. And then in principle, this is done for experimentalists. They don't think that there are databases with all these kind of things. You put whatever number here. You provide a Brillouin zone label, but it's arbitrary. It's not used by the program. You can put here, select for getting the basis vector and so on, with axial or polar. Axial vector always for magnetic structures. And here, we have also the possibility to use you see here, full physically irreducible peer and extended little group peer. This, when you click here, you read the database of isotropy. And then you can get directly the matrices used in isotropy. This is very important. For example, when you have a one-dimensional representations of dimension 1, and you are working with structures in which k is equivalent to minus k, then in such a case, the resulting magnitudes, for example, magnetic moment, should be real. And then you have to, and then the peer mean physically irreducible representations. They are normally when you have a pair of conjugate representation, it's easy to construct, but well, this is done and then transform to real form. This is done already in the database of isotropy. Then you have to provide a number. If you stop here, you put 0 atom, you will get only the representations of the propagation vector group. You can put also the atoms in unit cell. When you apply symmetry operators, you can, for example, put an atom which go outside the zero cell, the zero unit cell. In some cases, it's interesting to have all the atoms in unit cell in order to understand what we are doing and to have a set of atoms which is important for studying the particular problem you are working. And then finally, you have to provide an atom position and a symbol for the atom and an atom position, because the calculation will be done for this particular position. Then that's all. In principle, you have everything here. And we can, as I told you now, use isotropy if we click one of these boxes here. Isotropy database and fully reps. We can use that. Then the BalsIreps is just something for informing you. It's not intended to provide something for doing refinement, even if there is a part that can be used by PCR file, but it's not intended for that. There are other programs that do that better. For example, Sarah from Andrew Wise, that is prepared just for full prof, for instance. Here you see the output. Here is a particular simple case. I don't know what is that. I will do that now by hand. Well, let me just do that. I want to open here. I will open BalsIreps. What time is it? 11:15. 1 hour. I have 2 hours, no? I don't remember. Let me. Well, I open BalsIreps here. I will do that, for instance, for the case of. Let me just. I think that I have the lanthanum manganese. This one. Oh, sorry. I will open. This is Vesta. I associated that with Vesta, but well, let me just. No. I open that in an editor just to see which are the atom positions. I open that, and you see here, I am describing, this is a space group number 62, but in another setting, PB and M. Of course, if you provide that to the database of the irreducible representation, it doesn't work, because you have to use PNMA in the case of isotropy. But in BalsIreps, you can use still that and calculate the representation. Let me just do that. For instance, you have to provide first in which place we will be working. Let me just think I have here docs, I have conferences, wow. 2024, I'm in Dongguan. Talks, I'm in talk here, example here. I will take that directory and I will put here lanthanum manganese, like that, LMN. I will put here a title that may be whatever thing, it doesn't matter, it's not important, but I will put here P, B, N, M. And this particular case that will be treated by Françoise Damé this afternoon, I think, is lanthanum manganese. It's very simple. Yes, propagation vector 0, 0, 0. That means that you have the same periodicity, the magnetic structure, you have the same periodicity of the crystallographic structure. Then you put here is the gamma point. Normally you can put AM. We are working with actual vectors, and then the number of atoms is only one, manganese. And then I don't remember, I will have a look into the position of the atom that was here. Let me see. These are the unit cell. Here we don't need the unit cell for a moment. is 1/200. Then we come back here, we put here 0.5, 0, 0. We can put, if we want, atom in unit cells, and then that's all. You can provide also explicit sublatices for a particular numbering. This is important because the numbering, the ordering in which you see the atoms, in the literature, in the old literature, the people were using modes in the sense that G, type E, type G, A, etc. C, type C, type F. And then that depends on the order in which you put the atoms. And that is important. That is, if you want to reproduce exactly what you have in the literature, you have to use explicit Latin. But we are not concerned with that. Here you have the possibility to put short output or long output. Let me just use the long output, because in that case it's simple, but you will know all the calculations in detail. When you run BalsIreps like that, then all the calculations can be done just on clicking. You see here the calculation of the reps and the little group is based in the procedure of SAC provided within the program CAREP. This is what I use, a part of CAREP. But I changed some things inside, but well. The program is based in CrystFML. Then July, this is the version that, well, I don't know, I have not changed that, it's more recent than that. You have the symbol, the space group, the propagation vector group, the Brilliant Zone label at GM, the representation of GK will be calculated. Then information of a space group. This is exactly the same as you see when you use FullProf, because we are using CrystFML, in which all the symmetry operators and things are inside. In fact, all this is calculated. It's not a table. We calculate automatically, but it's quite fast. You see here, this is the PPNM. This is the corresponding Hall symbol, and the setting that we are generated from the Hall symbol. Here, this is what we are using here. And then we have the symmetry operators here in the Jones faithful way, just X, Y, Z. And here you have the element, symmetry elements. It's a binary axis along the X with a translation which is 1/2 here, and this is the position of the binary axis. You have all the information is here. Number of generators of the space group is this one. You can see here translational coset representative of a space group PBNM. These are exactly what we have here. Equivalent positions is repeated sometime here. The lattice symbol is OP. Conventional K vector is 0, 0, 0. The generator of the little group of the Brilliant Zone point GM are exactly the same, because all the symmetry operators of the space group live in variant 0, 0, 0. Then GK corresponds to the representation of the space group directly, because it's the same. Then you see here, number of elements of GK, 8. This is what you have, element of GK. Of course, coset representative is the number of elements of GK is infinite, because you have a translation. And here we have a number of irreducible representation of GK, 8. And you have the dimension of the 8 representation. All representation are dimension 1. And you see here another way of things like that. You have the symmetry element, this one, and use matrix of the different irreducible representations are here. Something is wrong here in the long output. No, it's here. It's because I don't see it. One, you have a just different, but we have another way of seeing that. This is, you have also the Kovalev representation of the rotational part, but it's not important at all. It's much simpler to see this way. This is the table of representation. Of course, you see here, IREPS 1, 2, 3, 4, 5, 8. Now, we can use a particular label of the representation when we go to tables in order to identify, because, for example, the representation 4 here is not the representation number 4 in isotropy, it's another one, and the number is different. Then, if you provide something using BalsIreps, of course you have to provide that, because otherwise the people don't understand what you are doing. When you say gamma 1, gamma 2, gamma, well, it's nonsense. This is just arbitrary because we are providing the representation. You see here, each symmetry element, here you have a sort of set notation, the elements like that, and you see all the characters, because we have a representation of dimension 1, they coincide with the characters. And another important thing is that even here, there is a rule, which is, there is a correspondence with magnetic space groups very easily here, of type 3 in that particular case, because it's k equals 0. Then, for instance, the first representation, you have all the characters equal to 1. That means the magnetic space group is BNM dot 1. I put the dot, just put so, because we are using the how you say, the PBNM with P capital, of course. Oh, sorry. Oh, sorry. No noise. Yes. PBNM.1 is a colorless group, but it's a magnetic group because we are considering here. Here is nothing which is magnetic. The just representations are the same. The only thing in the context we can attribute to that this space group. In this, the second representation let me just put PBNM. And here you see the elements, PB and M. The generators are here at the end, and you see the character is what you have to prime. For instance, this one is the B, and here B is prime. You see that. And N is this one, is also prime. And M is this one, is also prime. Then you have the magnetic space group of type 3 directly from the table of characters, because this is a very simple case. In other cases, it's more complicated, but you can automatically that data. Let us continue to see the output of BalsIreps. Here, you have more information, this propagation vector group information in another way. The input is the propagation vector is this one. K is equivalent to minus K, and the extended little group is GK. It's exactly the same. Well, you have some information, and you see here the application of the symmetry operators to this propagation vector give always invariant. And you see K equivalent minus K. And GK has the following symmetry operators, is all of them. Now, data about atoms. Then, up to here, we have all the information of the matrices and the propagation vector group. Here, now, we put atoms in a particular Wyckoff position, and then, instead of having 8 atoms, we have 4, because there are some symmetry elements that leave the position invariant. And then we ask the program to put all the atoms inside the unit cell. then you see here no negative numbers here. But you see the translation associated in order to bring the atom to the unit cell. Then we have numbers in a particular order that depend on this, how the symmetry operators are stored. And then we can do, this is what I was doing by hand always. All the calculation, for example, you see symmetry operator, atom number, character, etc., etc. The atom, here, for example, the identity, the atom 1, 2, and 3 are not changed by the symmetry. This one, for example, the symmetry operator, which is a binary axis along the z-axis, change the atom 1 in atom 2, the atom 2 in atom 1, the atom 3 in atom 4, etc., etc. And you see here that you can write that in a form of a matrix, which is a big matrix, that corresponds to the permutation representation. And then you have the vector representation, is the axial representation. You see here, you put here mx, my, mz, and you see here what you have. You will see that, for example, for a plane, here, you see that the operator is x, y minus z plus 1/2. And then the moment changes as minus mx, minus my, mz. This because it's multiplied by the determinant, it's the axial representation. And you see here, and you calculate the permutation and the vector representation, the character, etc., etc. Then you can use this formula that I show you for calculating the magnetic representation, how is decomposed in irreducible representations. And you see here 3 times irrep 1, 3 times irrep 3, 3 times irrep 5, 3 times irrep 7. Then not all the representations are active for this particular site. This is the important thing. Here you can put exchange. This is another concept that I will not enter here. And you see, well, there's some explanation about what we are doing and what is the convention that we use for the magnetic moment as a Fourier series using SK vectors. And these SK vectors are in general linear combinations of the basis vector. Then we can calculate the basis vector here like that. Then for representation, site number 1 and basis function is a projection operator, only non-null functions are written here. And we see basis function of representation 1 of dimension 1 containing 3 times in gamma. Here ISO name is not given because I have not read the database. Here you see this is the atom M1, M2, M3, and 4. And you see here the basis vector, one basis vector is this one. That you see that is along the x-axis, along A. And you see that this is a plus, minus, plus, minus. This is, for Y is plus, minus, minus, plus. And for 3 is, for Z is 1, 1, minus 1, minus 1. That corresponds to the magnetic space group P, B, N, M dot 1. Then you have automatically the ways of working. And you see also the operators. Here you see in general expression of Fourier coefficient of the atom non-related by lattice translations. When I put here may be complex, it's only for the case of incommensurate magnetic structures. For commensurate structures, all these U, V, W, which are the coefficients of the basis function that are in full probe are called C1, C2, etc., are general numbers that are real. And here you see sim, you see how the things are. These matrices that can be interpreted as rotational matrices correspond to a particular Shubnikov group, particular space group. Then you see for each representation how the things are transformed. If you consider the Fourier coefficient that in our case are directly moment, magnetic moment, because k equals 0, that means identification between the Fourier coefficients and magnetic moment directly. You see here how, going from 1, 2, 3, 4, how the magnetic moments are behaving. Then you can have a look on all these kind of things in detail, and you see what is the general output for BalsIreps. I don't know if I have a who is you are here. How long I have been? I will probably 11:34. I will take 5 minutes rest just for drinking a little bit water, and then I continue. If you have some questions, ask matrices also directly, and you can put that easily. One important thing is when you have several sites in the, because the BalsIreps is calculating for a particular site, but you have several sites which are different site symmetries, and then the basic vector will be different, etc., and maybe complicated. There are some tricks that you can use in full prof for using that directly. But you can, in general, one way of working is just to put here a general atom in whatever position. Then you will see now, if I do that, in that particular case, I put an atom in no symmetry, just in a general position. When I do the calculations, what we obtain is the list of matrices of the Shubnikov group directly. Why? You see here, well, this is, I will pass to all the things. Here we see now the full set of symmetry operators of the space group, and here you have a UVW that correspond to the rotations of the magnetic moments. And then you can see, for instance, this one, in this particular case, we have a X. This is a binary axis along X, and you see here, it's a binary axis, no problem here. There is no association with the, no, because this is the representation number 1. Let me just go to another one. And for instance, here, we are looking here for the binary axis along the x-axis, and you see that this matrix is different here. It's because you have the determinant of this one is, the determinant is 1, and then, but you have here minus. Then that means that this is an operator which is prime. Directly you can see that from here. If you want to convert that to particular setting, which is more or less complicated, and you can work with these kind of things, you can work directly with these coefficients. They are the Fourier coefficients. This number that you have here can be interpreted also as a rotational matrices that you provide in the full prof program. You can also put more complicated things. Let me just here. For example, if I go to extend the liquid, well, this is the same. It's not a problem because it's in such a case, 0, 0, 0 is not a problem. If we run that, putting here, it will look for the matrices in the isotropy database. Oh, sorry, I have to close. Oh, yes. No, it's okay. Warning, the writing of the reps from the database, pure data has failed. I say that because I'm using a general setting which is not PNMA. And that we have to use PNMA in order to do that. You can do that and then retransform by hand the things, but well, here you have to use then even if I have provided to read the database, it has not been read. Let me just put here PNMA. It doesn't correspond to what I have here because I put here a general atom. If I do that now, I put here extend a little group, for instance, or peer is the same in that case. If I run that, you see here, the representation of the extended little group has read from the input file, an input file, but the program has generated something from the physically irreducible representation database peer data txt version 2011, I think it's the latest one. Harold Stoke and Brandon Campbell, 2013. Here we have now the representations with the names according to Cracknell-Davis, Miller, and Love. This is what is used in isotropy. Then we have all the representations with a name which correspond to the... now, if you look for this representation and you compare it with the representation before, the order is not the same. That is, then you have exactly the same thing, but now in a standard setting. You can do that quite easily. Let me now complicate the things to see what is the problem when the direction of the order parameter is not defined uniquely, like in the case of one-dimensional representations. Let me just put here, for instance, 1/2 here. 1/2, 1/2. If I put that, let me just put here short output, it's not necessary to do. We will have already two-dimensional representation. Let me just, I will eliminate extend the little group now, just for doing the calculation as they are done in BalsIreps from the original way, PNMA here in that particular case. If I do that, you will see now that the representations here, they are real, no problem. Here, this is not a problem. They are real. And you have a two-dimensional, no, not real. You have here imaginary component. Then, because in BalsIreps, when I do the calculation using the THAC method, I don't look for unitary matrices transforming that to a real form. This has been done by the people of isotropy, and then we can use the isotropy case. And then you put here extended or fully reproducible representation. It doesn't matter, it's the same here. You run it, and you come back here, and you see now the representations are all real. Immediately. This is representation T1, T2. There are two representations of dimension 2 for the PNMA space group. And, well, we do exactly the same. We calculate, and you see here now, I put a general atom position, and then we have a lot of basis vectors. Yeah? Here we have 12. The representation 1 is contained 2 times. The representation 1 of dimension 2 is contained 6 times. 2 by 6, you have a general case with 12 basis vectors. This is impossible. Normally you need only, in that case, only 3 numbers. But you see here, how are the coefficients? Very complicated thing. And this is the advantage of using isotropy group, a classification of how you get these basis vectors. Then you have a lot of coefficients here, and then you cannot work with that in general. You can do the work before we had all the development of the isotropy. I was doing that by hand. I was looking for different symmetries, just looking at these coefficients here. And for a particular position, I was deducing constraints when, for example, suppose that the atom are in a plane. Let me just recalculate the things here. If I put here PNMA, I put here 25, 0.25. This is a special position. And here we have a lot of coefficients also here. You have QR, QUR, which you see here. And then they are disconnected. This is a splitting of an atom. We are using, in that case, for that particular position, in fact, that indicates you that we are putting atoms in two different positions that correspond to a space group, magnetic space group, that splits the atom position. Then you can do many things with BalsIreps, but you have to know, and that is complicated for the normal users. It's very complicated for that. And this is using, well, I use here this is, in fact, well, there are some people working of kernel and epikernels, like as in the case of Jana, that correspond to the kernel, just the most lowest symmetry if you use all these coefficients alone. But you can put constraints on here, and then the problem is that in BalsIreps there are not the tools for determining the possible groups. You can do also in BalsIreps calculations for incommensurate structures, etc. That is much more complicated in some cases. In other cases, maybe even simpler, that uses the magnetic space group. Well, this is something that you can try. Then I will present a case using isotropy, because in the case of commensurate magnetic structure, the combination of magnetic space group with representation is quite powerful and very interesting from the point of view of the physics of the transition, etc. I will do that now, and then you can repeat all this kind of thing, because there is an exercise in the what I put is normally distributed. You can have that, and let me just remove that on BalsIreps. Here is the holmium 2 barium copper oxygen 5. This you have an example which is I don't remember. Let me just working. You know, is isodistort. Charla. In the exercises, you have many things. Of course, we cannot do that. But there is a case, which is this one, holmium 2 barium copper 05. Here we have data from constant wavelength and time of flight, WISH. And you have a CIF file, and you have also the publication in physical review. It corresponds to the so-called green phases. The green phases were discovered in some sense, not really rediscovered at the moment of the high TC superconductor, because they are contaminating the APCO type of compounds. And this one is interesting, and we have published that in Physical Review relatively recently, even with very old data, using data from WISH and from D1B. And this phase is like that. You have a copper in pyramidal positions, and you have a raw earth. Here is dysprosium, but well, it doesn't matter. It's the same for holmium, exactly the same. And you have two types, dysprosium 1 and dysprosium, or holmium 1 and holmium 2, two types which are similar from the point of view of the coordination polyhedra, but if you look the surrounding of copper atoms, there is one in which you have only 3 copper ions, and the R2 are surrounded by 6 copper ions. And the behavior of these two sites is quite different from the point of view of the magnetic structure. Then these compounds, the interesting things, they are magnetoelectrics, and under field they become multiferroics in some sense. And these are, for example, the physical properties of that. We will have a look on that, the holmium case. We have a first phase transition, which corresponds to the appearance of a propagation vector, which is 0, 1 half 0 in the PNMA structure. And below, we have another transition in which another propagation vector comes, which is 0, 0, 0. Then we have two propagation vectors, 0, 0, 0 and 0, 1 half 0. And then you have a series, well, the physical properties you see here, that you have a metamagnetic behavior under field, etc., etc. You see that under field, you make appear polarization in the low temperature part. And if you remember here, sorry, in that part, there is no polarization, appears here, below here. Then these transitions make the compound, when you apply a magnetic field, you make appear a polarization. Then it was interesting to study these things. And when you have a look on the diffraction pattern in D1b, it's very nice. You see, oops, sorry. You see how are the things. This is the low angle part of the holmium baryon copper 06 observing diffraction pattern in D1b. And you see here that there are peaks, small peaks appearing at a certain temperature in which you have can be indexed as 1, 1 half 0. Then that corresponds to the propagation vector 0, 1 half 0. That corresponds to these peaks, in fact. Then going down in temperature, the holmium orders in some, and then the order is the propagation vector is 0 because this corresponds to the 2, 0, 0 reflection. But the 0, 1 half 0 is conserved also, and holmium contributes also to this kind of atom. Then you see here how are the things. And then you can refine, here is a wish, we can refine the data using the Rietveld method or using the magnetic space group. You see here it is a high temperature. 8 is PB21 over, I can read better here, N. This is the BNS notation. And of course, this is a type 4 group that cannot have, for example, linear magnetoelectric effect. It's impossible. This is the reason why you don't see that in this temperature, which is 8 Kelvin. But when we go, so this is the magnetic structure of that. We will see that how we arrive to that. When we go to lowest temperature, the group is here. I have changed it. It's not the standard one, but it's P1121 prime A. This is of type 3. And this one, even if you see 2 prime over A, you think that is centrosymmetric. It's not centrosymmetric because it's associated with time reversal. And then it's magnetoelectric directly. And you see here, this is the wish data in Q, because I prefer that. And then you see here in blue is the nuclear contribution. You see the magnetic part is much higher than the nuclear part. It's because the holmium has a huge moment. This is what then how we arrive to all this kind of thing, and you can see, this is the interesting thing. I will show you how to arrive to that. Let me just, before it was like that. This is the result that we have. Then you see here the magnetic groups of these two parts. Here is the transition. And here, you don't see, the moments, the magnetic moments, the component of the magnetic moments. But you can also have, I don't know if I have that here. No. Well, I have also the it's not here, it's probably in the article. Let me just verify. Yes, this is the supplementary information. You see the representations, and this is something which is interesting, because the primary representation here are these two ones, MY1 and MGM4 minus. But you have another one that appears due to the fact that we have symmetry, that it was not expected, but you do the calculation with these two representations, and this one appears as a consequence of the magnetic space group. And then you see here the different amplitudes that can be refined, and you see how they evolve directly as a function of temperature. I think that this is a very nice example that you can read, because it's in Physical Review, and you have already the article and the supplementary information in order to get all the information here and to have a look. And you can reproduce exactly that, because you have all the data and you can work, etc. Then this for you is something which is interesting. If you do that with BalsIreps, you can do that also, no problem. But in BalsIreps, when you we will ignore, for example, the well, we are using these two ones, but this other one will be completely ignored. That you are using just these two representations. In BalsIreps, you have to use 0, 0, 0 and 0, 1, half 0, and do the calculation, and by hand combine everything. It's a little bit more complicated, but that when you use, for example, isodistort. Then I will show you, I prepared just yesterday something just for showing you how to work. Then that corresponds to, these amplitudes correspond to the coefficient C1, C2 that you have in BalsIreps also. But here is much better control, because you have not only the primary representation, but also secondary effects that appear from the fact that you have a particular magnetic space group. In BalsIreps, you work always with the parent setting. You don't, because we are not using the concept of the invariant symmetry, we continue to work always with the unit cell of the parent space group. And then the basis vector are referred to the parent. In the case of isotropy, the basis vector will be referred to the basis of the subgroup that we are working. In the double, in that particular case, is a double unit cell. Let me just show you how you work with isodistort. For example, for that particular case, you can reproduce that. I will do that to show you how this is. The first thing, I suppose that Branton will explain that in much more detail. But it is something which is really simple. You have to load a zip file. Let me just select laser point. Here is the zip file that you have in your directory, the corresponding directory corresponding to holmium 2 baryon copper 05. You browse, you that, and you say OK. This is what you have to do. You say OK, and then after that, the program shows you another dialog, and you have to put, for example, displacive, holmium, copper, baryon, oxygen. All the atoms may experience displacive mode. And only magnetic is holmium and copper. I remove here this strain because there is nothing special here. And you have to click here before going further. in order to accept that the program will be calculating all these distortion. This is in the language of isotropy. Here, another important thing is use the method 2, general method, search over a specific K point. Then you select the gamma point, which is the propagation vector 0, 0, 0, that appears at low temperature. And then yes, it's selected. And the other one is the propagation vector 0, 1, half 0. And when you do that, first you have to click here and change number of superposed IREPs. Then we will superpose 2 IREPs. One is for one propagation vector, another one is for other propagation vector. And you have to click in change before continuing. Once you have done that, you enter in another dialog, which is select IREPs. You arrive to something like that. Space group, but you have all this information is repeated each time in the heading of the dialogues. You see the K point is GM, K. This is the Kovalev notation, K19000. K point is Y, K20 in Kovalev. And then you see choose if superpose irreducible representation and order parameter. This is optional. Normally you never click here. You just say OK, and you will see now the different order parameters, directions. Here, this is the solution. In fact, you have many complications. When you are working with magnetic structures, always select M, because you have the same representation, but corresponding to displacive mode, etc. And then the important thing is that if you select something which has no M here and M here, degrees of freedom are forgotten. Then you have to be very careful, because these include also the displacive mode. Now, this is the select order parameter. Right? You, at the end, when you click here, you have selected 2 representations. You say OK. You arrive to this situation, and then select the order parameter direction. And you see here 3 options. You see that you have a P11. All this notation can be found in the information of isotropy, and this corresponds to this to a particular type of so-called the images. And here you have the order parameter for the first irreducible representation, which is this one, which is one-dimensional. Remember that we were looking before in the PBNM or PNMA and 0, 0, 0, all the representation are one-dimensional, and there's no option for the order parameter direction. Is only one, no problem. But the second one is 2-dimensional, and you see here B0, BB, and BC. This is the general case. This is the lowest symmetry, and the highest symmetry is this one. This is you see here the magnetic space group, and an important thing is that you have the basis has changed because they use a standard way of working, and it's not what you have in your input parent structure. Then you have all this information. You can see that here. When you click on OK here, you go to see what to do now. You select order parameter. You have selected the representations. Of course, if you develop this dialog, you will see that you have many options. In many cases, you have many options. That is complicated because you have to test everything one by one. And it could be very interesting if the people working in the ISOD store are able to do something more, just download everything. Because we can write scripts and do that automatically. Well, when you click on OK here, you arrive now to that. What to do? Then you have selected a particular space group, and one important thing is, this is just a suggestion that I have, is that copy this for naming the PCR file. I copy that because you have here all the information about what you are doing, because when you have to test many cases, you get lost completely because the download is called always fullprof.pcr. And then it's the same name. And then in order to save that with different tests, you have to, I recommend you to copy that. You will see. And then what to do? Then you have many possibilities, save interactive distortion. Well, Branton will explain that in more detail. But I'm interested only in the part concerning with fullprof. You see that you can also export that for Topaz on fullprof. And when you click on OK, if you do that, immediately you will change the setting. In the general case, you are changing the setting all time. And then be very careful, because it's important to always, if you know what you are doing and you prefer to use another setting, no problem. But in general, in many cases, that, for example, is orthorhombic, and then you are used to work with a particular structure, then it's interesting to conserve that. I will show you that the two cases, when I select the standard setting, because the standard setting in what we have some, let me just go up a moment, is a monoclinic space group. In the monoclinic space group, the standard setting may be very complicated, and because there are many possibilities. And then in that case, it's not so complicated, but well. We do that, and I recommend at least at the beginning you can, if you don't, you see here, for example, that the standard setting, when I put here, I select that, select the setting, and here you have a 0, 1, you have a change of the origin. There are programs that can work with, in the case of fullprof, you can use whatever setting, there is no problem. But there are programs that do not work properly with other settings. And then I recommend, if you want to conserve exactly the same origin, you can remove that and put a 0. And then here is just the multiplication of the unit cell by 2 along the p-axis. Once you have done that, you have selected the setting that you want, then you click on OK. After selecting the radio button fullprof, you click on OK, and then the program, now you click on OK, and the program, save. And the program gives you always here fullprof.pcr. And then if you download several times, you will crash for different options. You will not be able to work with that. And then what I do is just to paste. But remember that this was the original copy that I told you. Where this up to here, the .pcr is otherwise. But here you see this is P21 prime over C. We have a blank here, white blank space here, etc., etc. And you have also the pipe symbol in Linux, for instance. And then all these things, the pipe and the slash, are forbidden as names of files. You cannot use that. And then what I do normally is just compact everything, replace the pipe by a minus sign here, because it's for separating the first representation from the second one, order parameter direction. Here is the name, the number of the magnetic group. I put that together. And then in between the number and the name of the magnetic space group, I put an underscore. And the slash I replace by underscore over underscore C, to say P1 prime over C, PCR. Then I modify that, you save, and you get a PCR file which is complete. Let me now show you how is the PCR file generated by IsoDistort. Oh, I don't know where I am now, so. Yes, PCR file generated by IsoDistort. This is a template. It's not adapted to your calculations. It's just a template. The important part is this part. You have to, and you see here the description. This part corresponds to the description of the structure that you input in the zip file, but refer to the basis of the subgroup, in which we have a double one unit cell parameter. And you have here the different sites, etc. Well, it's more complicated than in standard. And here you have the following thing. Polarization vector of symmetry mode for each atom. That corresponds to displacive modes. And you see here vectors, which are, we call that polarization vectors, but well. And here you have a number that makes reference to the amplitude that we will see below. The name of the atom, the irreducible representation that is being considered here is GM1, that is exactly, all these GM1 correspond to the crystal structure of the PNMA. If you put 0, all the others, you will get exactly the PNMA as before. Then you have here the basis vectors. These are the basis function of the reducible representation normalized in a very particular way, which is related with the fact that you can put the amplitude directly in angstroms for the displacements. That is what we have here. A lot of numbers, but you don't have to work with that just to see that there is a lot of things. And here you have a basis vectors of magnetic symmetry mode for each atom. And you see here the particularly reducible representation, and you have up to 80. You have a lot of, you have 36 amplitudes. There is a lot here. The problem here is that the normalization that we have here is not very convenient. Then you have the possibility in the full prof, I will show you now the real PCR file that I use. Here you see, well, there's 2. We have to change, this is something that you have to be careful. You have to change this for 3 because it's a Holmium 3+. It's not Holmium 2+. Copper is okay. MCU2, well, then you have it. Then the full prof will use this space group information and this for reading the database of provided by isotropy, and then I have the symmetry operators of this group in the standard setting, and I transform back to my setting using the inverse of this transformation, and then you get the proper things. But you don't have to worry about that. And then you see what is the setting we are using really. Is from parent is A to B, C. Well, 2 is the same as 0. It's not a problem here. It appears 2 is because the calculation performed by isotropy gives you an integer number for this. but it doesn't matter. You put 0 or 2, it doesn't matter. Then you see here all the coordinates generated in that case. And here we have the vectors. Then the program full prog will give linear combination of these basis vectors with these coefficients. These are the coefficients. With, for example, these are amplitude of symmetry modes. This is for angstrom, maximum amplitude 0.3 angstroms, for instance. You can limit the variation if you refine to be maximum 0.3 angstroms in order to, if you have a lot of oscillation, because you can refine that. Amplitude of magnetic symmetry modes, you put here whatever numbers, it doesn't matter. But normally, if you don't do anything, these amplitudes are not in Born magnetons, are in something related with the unit cell parameters and Born magnetons. That's all. Then you can use this file, provided that you know. Well, it's relatively simple. You have just to copy that, change the profile parameters and the things related with your particular instrument, and you can run that. Let me show you what I have here already. This is the particular case that we are doing here. This has been modified already. And then you see that, in fact, we can put here magnetic moment and forgot completely the amplitudes. That is interesting in the case you want to put, for example, some magnetic moment equal to another magnetic moment, the amplitude, or the modulus of the magnetic moment in different sites. Because with the amplitude, you cannot put a constraint like that. And then you can use, for example, spherical components of the magnetic moment here, combined with the amplitudes. And then in such a case, you have to put all the amplitudes of the magnet. Here, I have put the amplitudes. I have introduced a keyword here. You see the name of the phase. Magnetic mode. I fix X, Y, Z because you cannot refine that, because what we refine is the amplitudes. And you put here this common reference cell. And then this is the cell, the double cell, that we use when we calculated the basis vector. Why I put that? Because these numbers that we have in the magnetic part here, symmetry mode, these numbers, we want to have this number in Born magnetons. And then I have the program will calculate from the normalization without changing you see here, I have calculated coefficient in the basis vector of magnetic symmetry modes for each atom. This coefficient is for correcting this normalization that is performed by isodistort, which is not very useful because you don't understand the amplitudes. Is much convenient to have that in Born magnetons. And here you see that I have refined the crystal structure because the case I'm using here is not time of flight, it's D1B. In time of flight you can put more, but it's, even you obtain nearly the same. Here we are using the symmetry modes, is displacive, that correspond to small departures with respect to the parent structure that we use, because we are at a lower temperature. And but I forgot completely all these amplitudes. If you want to explore, for example, magnetoelastic things, you can start to refine amplitudes here and to see if they are significant. The major part of the cases, the amplitudes are smaller than the standard deviation because it's very difficult to determine. There are other cases in which you can have that, but it's not in the general case. And then for having the amplitudes, the magnetic amplitudes in ball magnetons, you remember that you have to put here by hand this reference cell, the unit cell that was in the zip file you use for isodistort. Then you can run that. I will run that immediately here just to see where is. No, this is another one. No, let me just go to the directory in which I have exercises. Then normally you should have all these things. Go to holmium, constant wavelength, sequential modes. No, I have an example. Here is more complicated. Let me just go to the talks. Examples. Here's one. I think it's here. If this low temperature, this one, I have the data file in the same directory. In the exercise, you have the data file in another directory in this, and then you can run in sequential mode in order to see how the things can change. When you do full prof here, it will run directly because the refine is very good. The magnetic R factors and everything is good here. You see, here is a small. I think sometime you have here two small peaks that correspond to the vanadium thing. Then you have represent that. You will see the red. I think that the red are magnetic, purely magnetic, and in other cases you have a combination of the two things. And if I think that I have here the sub. No, I have not. Let me just verify. Well, that doesn't matter here. I have two more reflection here. But the fit is very good, of course. And you can see, this is the standard. The actual setting is, well, I have changed. This is monoclinic with the C-axis along C in the setting we are using. Then when you run that, you see, for example, the Vesta file. For example, you can see GM1, GM2. This one, for instance. Let me just verify. Yeah, this corresponds. Let me just remove things. We got every objects. Remove the DOM. Here, you see the magnetic moments here. The small things are copper, and the other are holmium. There are two types. Of course, you can go now in Vesta, try to put different colors, etc., in order to recognize something. It's unfortunate that Vesta puts all the moments in the same color. You have to go and to put something more. But you see a strongly non-collinear material, the magnetic structure, and well, you can refine the magnetic structure using modes and representation simultaneously. Yes.
Said that secondary mode.
No, you can remove it. No, I put that because you have that, and it is totally negligible. In fact, if you do that with BalsIreps, you don't see that at all, and then you get the same refinement using basis vectors in BalsIreps as this one. The advantage here is that you have the possibility, when you have a strong magnetoelastic coupling, in that case, you can refine this plus. Even the magnetic is not relevant. I don't remember now, but well, you will see here. I probably put something, but we will see. For instance, Yes. This is amplitude of yes, it's the R magnetic here. The important one is this MGM4 minus here. I put here, you see that they are not refined, M3. If I try to refine, well, let me just try to refine one of these amplitudes. And you will see. I put here 1, and then I will refine. Here, these are, except one of them, we can try to refine that, yes. For instance, you will see what happened. Normally, it will oscillate. Oh, divergence. In that case, even you have divergence, because probably I started with 0, and then the derivative is not well defined. And let me just see. No, that was, well, let me just verify that I hear. Yes. Because in ball magnetons, let me just put 2 ball magnetons, or 0.2 ball magnetons here, just to see what happens. Well, it's converged, but you will see now. We go to the results. Well, I was working in another place. Let me just come here. Exercises. No, it was in talks. No. Example, no. Sorry, no, it's because I was in another directory, because I am doing plenty of things. Creative file, no. And here, we have here, these are the results. I open some summary. And here, you have, for example, final atomic position calculating from symmetry mode. We have here here is global amplitude representation game 1. This is global amplitude representation I1, etc., etc. Different things. But let me just see. Well, you see him immediately. Amplitude candidate to be nullified because the sigma is much bigger than the other. And here, yeah, seems to be, but it's nearly negligible. But here, in principle, the sigma is slightly less than that. But the program tells you that there are amplitudes that may be nullified without changing too much. No, here, the structural models, yes, but they are just the gamma point. It's the same. Here is the structural points are here. I have gamma 1. That corresponds to the structure, the normal structure. There is no additional, it corresponds to the PNMA directly. Then the different IREPs here, the secondary modes here, I have not enough resolution here for exploring that. If we put that, it's going down. But this is the interesting thing, is that you can look for this kind of possibilities using the combination of the magnetic space group with the representations. I think, well, it will stop here. I don't know how long. It's okay? Thank you.
Thank you very much. So now we are lunchtime, so pretty quick question. Something. So we may be able to have a question to the during his stay at the lunchtime afterward or something. So in this what I said before evening, we again will have some question time. Okay, so let's thank Yang again. Thank you very much.
Thank you.